New topic today, vector fields and line integrals. It's a fairly easy section since it's introducing new material. Some hard stuff last chapter. More integrals. Well, we're almost done. Look at what you've got here. This is what I used to have to carry around as a graduate student. Table of line, of integrals, series, and products, all these things. Aren't you glad you have electronics now so you can just look it up online and not have to carry this tome of a book? But we'll do a little bit more with integrals. We'll do line integrals this chapter, and we'll also do vector fields. Today we'll just do the vector fields, and we'll get on to the line integrals involving them. We did multivariate calculus. Now we're going to do vector calculus here. So, like I said, this part isn't so bad. A function that assigns to each x, y in a plane region a vector is called a vector value function, or a vector field. For instance, if you give x, y to this function f with an arrow over it to indicate it's a vector value function, it is some function of x, y multiplying I, the unit vector in the x direction, plus a function of x, y times j, unit vector in the y direction. So you get back then an arbitrary vector, right? By putting in an x, y, you can specify that you get back at each point a particular vector. So associating a vector with each point in a plane region makes it a vector field. Kind of like this, right? At this point, here's this vector. At this point, here's this vector. So this is a sketch of a vector field where at a bunch of representative points that we pick, we draw a vector like that. Now, we can do these in any number of dimensions, of course, right? This is a vector field in the plane. You could also have f of x, y, z equals three components, a function times I plus a function times j plus a function times k. Those are common in lots of the physical sciences, for instance. Here's a nice example just to illustrate that there are a few vector fields that come up a lot in practice that you should recognize when you see them, kind of what they look like. It's kind of like in algebra. You need to know, oh, that's a line, I'll put down my straight edge. That's a parabola, I'll make an arch. Right? So the same thing here with vector fields. There's a few basic ones you want to know. How do I know how to sketch this one that looks like x, this function, x over square root x squared plus y squared, I plus y over square root x squared plus y squared, j. I know immediately how to draw it. And I'll say it's on R2 minus 0. What is R2? I'm trying to introduce a little notation here too. That's fancy notation for the real numbers R, Cartesian product with the real numbers R. It's all ordered pairs of real numbers. It's just the plane. So this means the plane, take away 0, 0, the origin, because you get a division by 0 here, right? If you put in 0, 0. So this is a vector field on the whole plane except the origin. At every point there's a vector in, but you draw it like this, just a few representative vectors to give people an idea. How do I know it looks like this? The vectors are all pointing those directions and about those lengths. Well, here's y. This is my vector value function, x over root x squared plus y squared I plus y over root x squared plus y squared j. And the first thing I notice about it is I have a common factor here, 1 over square root x squared plus y squared. I can pull out and say it's this times this. And now this vector xi plus yj, to what direction does it point? Well, if I'm at the point xy, I'm sketching this vector, but at the point xy, the vector xy goes from the origin to that point. So this is a vector that points in the direction of xy, has components in the same direction that you came from the origin. It's just scaled by this function. So I know that at this point, at any point, I make the vector point directly away from the origin because it's proportional to the vector x with components x, y. So over here I go away from the origin, over here I go away from the origin. Every vector points directly away from the origin. In lots of applications like gravity, for instance, where you're pointing towards the sun, you put the point outside of the origin, you put minus x and minus y and scale it. Right? And so you have then all vectors pointing towards the origin as a common application. Same thing with charged particles. You're attracted toward a particle at the origin, then they all point this way, you get minus x, minus y. Now, how does this particular problem scale those? Well, if you think about it, square root x squared plus y squared is the length of this one. So I'm just taking this one and dividing it by its length It's a unit vector, right? So I know when I look at this, since I'm dividing this vector by its length, it's a unit vector and its direction points away. Vectors can be specified by their components. They can also be specified by what direction do they point, what's their length. I have to just sketch all unit vectors everywhere except at the origin, pointing away from the origin with unit length. So that's what I did here. Every vector has unit length and points away from the origin. So there's one you should recognize. Unit vector fields, one where all the vectors are 1 unit long. That's convenient for computer plotting where you're only interested in the direction and not the length of the vector. Direction fields in differential equations, for instance, do vectors all of the same length, possibly unit length. And lots of these vector fields, like we said, point towards or away from the origin. If you have fluid that might be pushing it away from the origin, right, coming out of a source here. So there's some reasons to memorize this kind of vector field. Now we can look at some others too, right? Suppose I, scroll down the page here a little bit. Suppose I take this one, f of xy equals minus yi plus xj. What's significant about this vector field, and how would I know how to sketch this one? Well, if you think about it in direction and length again, what's its direction and what's its length? Its length is square root y squared plus x squared, right? But that's just square root x squared plus y squared. That's the distance from the origin. So if I'm 1 unit away from the origin, the vector is 1 unit long. If I'm 10 units away from the origin, it's 10 units long. I make its length exactly the distance that it is from the origin. So here's half a unit away, maybe it's half a unit long. Here's one unit away, it's 1 unit long. Here's a vector 2 units away, 2 units long. Now how do I know to draw the direction that I have? Well, if you notice on this one, this comes up in rotational fields, like, rotating fluids and this kind of thing. In this particular case, if you think about it, the vector coming from the origin to the point xy, at the point xy, you have the vector minus yx, and the dot product xy with minus yx is minus xy plus xy is 0, right? If the dot product is 0, that means the two vectors are orthogonal. So I know that the vectors I draw all have to be orthogonal to the point that comes from the origin to their initial point, right? If at this point xy, I sketch this vector minus yx, it has to be perpendicular to the vector from the origin, right? This is xy going out, and I plot minus yx perpendicular to it. Then the question is, just does it go this way or this way perpendicular? Draw a couple of them, you'll see these actually go counterclockwise. If you put y followed by minus x, then they go clockwise. So these rotational things are also useful, and in this one, you just draw all the vectors perpendicular to the vector from the origin out to the point you're at, going counterclockwise, and its length equal to the distance from the origin. So that's how we can sketch that one. All right, well, let's try this next one then. There are some other important things in these vector fields. For instance, I can create a vector field using the gradient operator. This is a very important operator, we said, right? We call it an operator because it takes these functions to functions kind of thing. It actually takes a function in two-dimensional space to a vector value function in two-dimensional space in this case. But here's the two-dimensional gradient, and if you apply it to any function f of xy, it gives you back df dx df dy, a vector valued function. So the gradient of a scalar function, we call it an ordinary function, is a vector valued function. And you can do that in any number of dimensions. For instance, in 3 dimensions, if you have a function of 3 variables defined in 3 dimensions, then the gradient of that function is a vector valued function. So the gradient applied to functions gives you vector valued functions is one useful thing. We've already seen that before. But it can also be applied to vector valued functions, vector fields, by these operations, what that we'll define here. This is a definition. The divergence of a vector valued function or a vector field is del dot f. Upside down delta we call del, so that's called the gradient del. Del dot f is just, well, what should we mean by that? If we follow our usual notation, it's d dx dy dot f1 of xy, f2 of xy, the vector field. Maybe I better zoom out just a bit, huh? And so you take d dx of this one plus d dy of that one, and that's the definition of the divergence of a vector field. So we can also get back, look what we get. We get actually a function, right? There's no more I and j. You can take the gradient of a scalar function and get a vector field, or you can take the divergence of a vector field and get back a scalar function, right? It's just an ordinary function. That is df1 dx plus df2 dy. How easy is that? Divergence is very easy to compute, but it's actually very important in fields like fluid mechanics. How about the divergence of f in 3 dimensions? You take del dot f just with 3 components. df1 dx plus df2 dy plus df3 dz, just following the expected notation of the dot product. All right. So you can take the divergence of a vector field and get a scalar field, just a function. Then in addition, only in 3 dimensions, because the cross product is only defined in 3 dimensions, unless you're a theoretical physicist and do a 10-dimensional space with cross product, and there's a version of this in 7 dimensions. Curl f is gradient cross f. And so it's this determinant, ijk, followed by the gradient, ddx, ddy, ddz, followed by the components of f, f1, f2, f3. And so here, for instance, is a vector field. At each point xy, it gives you back a vector whose components are x times y times z, y squared minus x cubed. And what's the divergence of this vector field in 3 dimensions? Well, you just take ddx of this one plus dy of this one plus ddz of this one. There they are. ddx of xy is y. dy of yz is z. ddz of y squared minus x cubed is 0. And so the divergence of this vector field is just this scalar function, y plus z. Just an ordinary function. The curl of this vector field, ijk, the gradient operator, and the 3 components of f. And let's see, right, remember how to do these. For the component in the I direction, you wipe out the row and column y and put dd, take this subdeterminant, ddy of this minus ddz of this. So ddy of y squared minus x squared minus ddz of yz. And then minus, remember, this one, wipe out its row and column. And it's ddx of this one minus ddz of this one, and then finally plus k, wipe out its row and column times this determinant. This one, this, plus minus this and with this. So ddx of yz minus ddy of xy. And when you compute all those partial derivatives, right here you get 2y minus y, multiplying I. Here you get minus 3x squared, let's see, yeah. Derivative minus x cubed is minus 3x squared, minus nothing, because there's no z in there. And then 0 minus x. And so you compute all that. The curl of a vector field is again a vector field. So the divergence of a vector field is an ordinary function, but the curl of a vector field is again a vector field in 3 dimensions. It's this one with components yi, 3x squared j, and minus xk. All right. So those are pretty straightforward, just got to do the computations. And we'll see applications of those coming up soon. Let's let me move over on the spot here. Now, one of the important applications of these vector fields is that some of them turn out to be conservative, like gravity's conservative. Right? When you go around in orbit, you come back with the same energy you started with as an application of conservative. We're going to talk all about that sort of stuff in this coming up chapter. So we'll say this, here's the actual definition. A vector value function of the plane or in any number of dimensions, but we'll just write the definition for the plane and say it holds similarly in whatever dimensions you want. A vector field is conservative on an open region in the plane if for some function phi of x, y on that region, f is equal to its gradient. So a function that is the gradient of some, a vector field that is the gradient of some function is called conservative. And actually, this is a little different from what the physicists like to do. They like to think of f as a force and say it's minus the gradient of the potential function. So in their representation, they'll say it's conservative if it's minus, if the force is minus the gradient of the potential. So you'll see that sometimes with a minus on it. And call it the force against this. Well, f, here's a vector field, and we might say find phi to show that it's conservative. Can we find the potential that goes with its force within a minus? Can we find the function phi that shows that this is actually a conservative vector field f? Well, what we want in order for this to be a conservative force is that this has to be ddx of something and this has to be dy of something, right? So it's a gradient. So if we want ddx of phi to be this, 2x plus y, we want dy of phi to be this, x plus 3y squared, we can recover this, called the potential function. And so for us, we'll say phi is the potential that determines f. In physics, they might say minus the gradient of potential energy is the force. So our potential, such that f is its gradient, has to have this partial derivative. That means phi is the partial integral of this. Partial integrals, like partial derivatives, treat the other variables as constants. So we take the partial integral of 2x plus y with respect to x. That means treat y as a constant within this integral. Integral of 2x is x squared, but integral of y is not y squared over 2. Excuse me. We're treating y as a constant, so its integral is x times y, right? Integral of c is cx, but c is really y here. And then the arbitrary constant that comes out of this, since y is treated as a constant, is any function of y, right? So we know from partial integration that the potential for this vector field is x squared plus xy plus any function of y. I wrote h of y, where h is an arbitrary function. Similarly, since d phi dy has to be this, we can take a partial integral with respect to y and recover phi. Right? So we take partial integral of this, treating x as a constant this time. Integral of x is xy, right? Think of this as c. The integral is cy, but c is x. And then integral of 3y squared is y cubed, right? Y cubed has derivative 3y squared. And then there's an arbitrary function of x for the constant, k of x I wrote there. Now we know that phi has to be equal to this and has to be equal to this. Some of these terms match up. There's an xy in both of them, right? But this has an x squared. Well, that must be part of k of x. This has this has a y cubed. That must be part of h of y. In order to make these two match, the only function we can have is x squared plus xy plus y cubed, plus you could have an arbitrary c that doesn't depend on either x or y in there. But these are all the functions whose gradient is this. But the fact that we found this shows that this f is in fact a conservative vector field on the plane. And these are all the choices for potential functions, just like when you did integration in calculus 1 and you said, what are all the antiderivatives of this function? You gave them to within an arbitrary constant. This is analogous in more dimensions. We'll say whenever we come up with a conservative field, it's got an infinite number of potentials, but they're all equal to within a plus c also. So it's just following what you did in calculus 1. All potentials are now equal to within a plus c. Here's an example of a potential phi equals 4 ln r, where r is the polar distance to the point, root x squared plus y squared, right? What is the gradient of phi? Well, we just calculate it here, and the gradient of phi is d phi dxi plus d phi dyj. Well, what is that? That's by the chain rule, d4 ln r dr dx plus d4 ln r dr dy, right? R being a function of x and y both. So we apply the chain rule to calculate the gradient of this function of r, which comes up quite a lot in practice, right? Because you have lots of force fields that depend on r. So you got, well, by taking the derivative of 4 ln r, you get 4 over r. So this is 4 over r, x over dr dx, if you calculate that partial derivative, x squared plus y squared to the 1/2 is 1/2 x squared plus y squared to the minus 1/2 times 2x reduces to this. And then one nice thing here is, since it's symmetric in x and y, the partial derivative with respect to y is immediately the same thing, just interchange x and y as y over square root x squared plus y squared. And so here's the gradient, 4x over r squared and 4y over r squared. I got my last line cut off, I guess, but 4x over r squared, 4y over r squared is the gradient of this potential. This leads to an interesting thing that you see in lots of important applications, actually. Of particular use is this inverse square law. If you see a vector field like this, f of xy equals minus x over r cubed I minus y over r cubed j. This is a very important one, and it might be multiplied by some number, c or something. This one actually is called an inverse square law because why? Its length is the root sum square of these, is c times absolute value of c technically. Actually, let's tell you what, draw it here, say the length of f is the length of all this stuff. It's absolute value of c. Remember, when you have a constant multiplying a vector, the length of the result is absolute value of the constant times the length of the vector. And now r cubed multiplies the whole thing. You can take a 1 over r cubed out of here and rewrite this as 1 over absolute value of r cubed, because it's just a scalar value function. Length of minus xi minus yj is absolute value of c times 1 over, well, r is root sum square of x and y, so this is 1 over r cubed. And what's the length of this one? It's square root x squared plus y squared. It's r. So this is equal to absolute value of c over r squared. The magnitude of the force field is proportional to, that is a constant times, 1 over r squared. We say it's inversely proportional to the square of the distance you are from the origin. It's an inverse square law. So when you see that in the text, you know what it is. I did think of just a little bit more that should be said here. There's a couple of interesting consequences of these operations we've been talking about. Suppose you have del dot del cross f. There's a couple of questions like, what order do these have to be done in? Well, if you really think about it, if you do the dot product first, then you can't do a cross product because this hasn't got three components anymore. Alright, once you do the dot product. So it has to do this order, do the curl first, and then take the divergence of that. So you take, there are implied parentheses here for the order. And you can calculate this just like the other examples, like for instance, suppose f is this, 2xi plus j plus 4yk. Then we put ijk in the first row, the del operator in the second row, and then the components of the vector in the third row. And when we compute this with great labor, we take I times dy of this minus ddz of this, right, which is just a little determinant, this with this and this with this, minus j times wipe out its row and column, ddx of this minus ddz of this, there it is, and k times dx of 1 minus dy of 2x. And we calculate it all out, we get 4i, and then we got to take the divergence of this vector field. It only has one component, so we take ddx, dy, ddz, I left my dot out, let's put it in. Del dot this. Well, we're going to come up with ddx of 4, right, which is 0, plus dy of 0 is 0, plus ddz of 0. The whole thing adds up to nothing. And just seems like a coincidence, doesn't it? But in fact, there's a theorem that actually del dot del cross f is always equal to 0 for any vector field with whose components have continuous partial derivatives on a second partial derivatives, I should say, on an open region. The reason is this: if you calculate out the del definition, del dot this, how do you calculate the dot product? Well, that means each of the three components here has to operate on the corresponding components here, I, j, and k components, which means you could just put these into the first row and they would execute the dot product. All you have to do is compute this determinant. So here's a shortcut right here that we're going to mention again. We can just put this del as the first row, ddx, ddy, ddz, and that will execute the dot product with this vector here. And now you notice, if you have linear algebra before, you find that if you have two rows equal, what do you know in a determinant? It's 0, right? When any row is a multiple of another row, then you know immediately that the determinant is 0. And if you compute this all out, I didn't compute it, but you can compute the determinant. This one with this times this minus this with this, and minus this with this, and so forth. The details show this is actually always 0, provided they have continuous second partials on there. So there's an interesting thing. Instead of going to all that labor, you could have immediately written 0 because del dot del cross any vector field is always 0. Just like with vectors A, B, and B, or A, and B, if you took A cross B, you'd get a vector that was perpendicular to A and B both, and if you took the dot product with that, dot product of a vector that's perpendicular would be 0. Just like when we had regular vectors, if you had A dot A cross B, you always got 0 for that reason. This is perpendicular to A and the dot product is then 0. Similarly here, you would expect the same thing, and sure enough you do. And finally, get a similar term. Finally, if you take del dot del operating on a function, right, you can take the gradient of a function, then take the divergence of that. What do you get? You don't get 0. You get an interesting result that is important in lots of partial differential equations. If you go on to take that, right, you're taking ddx, ddy, ddz dot ddx, dy, ddz gives you d squared dx squared, d squared dy squared, and d squared dz squared, all operating on f, gives you this, d squared f dx squared plus d squared f dy squared plus d squared f dz squared. It's called the Laplacian of f, and that will turn turn out to be very important in later applications.